We're going to start this afternoon session with Teare, which is a professor of biostatistics.
Thanks very much. First of all, can you all hear me? Great. So thank you very much for inviting me to this workshop. I was really delighted to hear there was going to be a workshop looking at the sort of reflection on the reproducibility initiatives and how can we move forward in this. So my background, I've actually been a statistician for quite a long time. I started working in cancer genetics before BRCA1 and BRCA2 were actually discovered. So I started working in genetics when family-based studies were, what do you need to do? You collected samples from families. The data that you got was very, very restrictive. You had to do the best with what you had. And I worked for about 15 years in that area, which involved working very closely with people in the lab that were generating the polymorphic variants and the data, and us having a really good understanding of all the elements of what was going on. When the field sort of moved more into population genetics, I also moved post, and I ended up working more broadly in epidemiology and observational studies. And I realised that I'd sort of grown up in quite a closeted environment where I was used to speaking to people that all really well understood what was going on in the system. It was a fully integrated team, and I found it was much more difficult to really be able to work with people and advise them about statistics if you didn't really fully understand where they were coming from. If someone just approached you and came with a lab book or came with some ideas, it could be very difficult to give them what you would call really good quality advice. You could certainly give them advice, but I always felt I needed to know a bit more to be able to give that advice. And then around 10 years ago, I moved post again, and I ended up getting involved in clinical trials. And initially, I was astonished at how much you had to specify in a clinical trial. First of all, to get it funded, but also before you were allowed to really do anything. And I really found it difficult to be able to say up front how I was going to analyse any data before I'd seen any data. I really found that very hard. Now I've been in the field for a few years, I can actually see why that's so valuable. And part of the reason is that it forces you to have discussions with the people, a bit like I used to have when I was first in research. So you all really understand what data you've got, what are the mechanisms generating it, and what questions did you want to ask of it. So what's interesting, I was sort of midway into my experience in clinical trials when we started to get interest from one of the major funders in the UK, the NIHR, which is the National Institute for Health and Care Research. And that body is like the research arm of the NHS, the National Health System. And they want to get evidence before they want to make a recommendation to be used in hospitals or in public health. And we started to get requests for helping researchers in the lab, in places where they didn't have easy access to statisticians. And so that was when I entered this field around about 2013, which is around about when a lot of these projects were going on as well. So that's why I'm here today, I think. So my talk, I'm going to take a little bit of a step back in my talk. It's massively coming back after such a delicious statistics. I do appreciate it. We'll just sort of remind ourselves what is statistics for, why we need it. I'm afraid we really do need it. Then a little bit about the context in which it's got a bit of a bad name, it's been used poorly, and then hopefully end up on some positive notes at the end about doing things better. So there might be some slides here that you remember from your sort of early days in statistics training, but it's always helpful to go back to some reminders, I think. So statistics can be thought of as a really broad toolkit of all sorts of methods and approaches. And it's used in many, many, many fields. But thinking specifically about what we're talking about today, it's statistics that's used in design of experiments and design of studies, but also in the analysis, which we're all familiar with, and also in drawing conclusions and reporting. So it's mainly important. These sort of toolkits help us present and summarize data. So we can't really avoid that. That's very helpful. And more importantly, the second one, this quantifying the evidence for or against specific hypotheses. So that's really critical. That's what we've had with our p-value discussions, and also we've seen already, we've seen some meta-analyses type things get presented today already, where we're basically using statistical methods to show together several results and make an assessment of how much evidence is there for or against a specific hypothesis. And then I think the real crunch of the matter is that statistics is actually, we tend to forget this, but it's really helpful and essential to help us make decisions in the presence of uncertainty. So while a lot of the time there's been some pushback saying we shouldn't have p-values, are very unhealthy, we shouldn't have these thresholds, we don't really live in a world where you can make a little bit of a decision. You have to jump. You either stay where you are and say, I don't think there's enough evidence, or yes, I think now there's enough evidence and I'm going to do this. And that's often what we're doing in our daily lives. We're generating data, analysing it, trying to get it published as best we can. But in order for a doctor or a funder or a medical team to decide to put something into practice, they want to be convinced first. And this is where I think it leads to a lot of, this probably underpins most of what we're experiencing at the moment, because we want a clear-cut decision or an answer. Have I locked it? Maybe I'm pressing the wrong button. It just moved on the screen then. It moved on the screen and not the phone.
Sorry about that. I'm going to check the mess.
You're going to have to look at that slide for a bit longer. That's why it's important, and that's why we use it. But it has had a bit of a poor reputation. And as has been highlighted this morning already, there's underpowered research going on. There's lots of problems in the field potentially, but from a statistical perspective, and that's what I'm going to be talking about, it's underpowered research. Underpowered research means you've generally got too small a sample to answer the question. You're not going to get reliable or meaningful results. Brilliant, thank you. actually skipped on 2 slides. This one was really just to say earlier. So we have got a really nice set of tools to help us support us in making decisions. But now statistics has really come to the front in the reproducibility crisis. There's also a lot of concerns about waste. Research waste was mentioned a lot today. If there is a tendency for not statistically significant results to get published, then those are never seen. This is just wasted information. All research will be generating evidence of some sort or other. It shouldn't just be lost. And we're sort of really in this reproducibility crisis because we've got a problem with our research culture. And I think Marcus outlined quite a lot of the pressures. It's not just single individuals, it's a whole culture. So from the stats perspective, the things that are coming to light from poor research practice for statistics, the underpowered situation, we're getting biased estimates. This could be due to biased sampling, biased analyses, biased reporting. We were having bias introduced potentially at many levels. Then the p-hacking, and this is some of these things that some of these terms are used to mean similar things. But the p-hacking tends to be that term's used when you do multiple hypothesis tests or varying a little bit on a theme, but then you don't say how many of those hypothesis tests. And while statistics can control really well for multiple hypothesis testing, it can't if you don't think about it beforehand. Now then, there's sort of related to this is the vibration effects and flexible analyses. This is when you might have a multitude of possible ways that you could ask the research question, and you're a bit vague about it. So you could maybe do a t-test or a non-parametric test. You've not said which of those you would prefer, and you can be adjusting from the variables used for the methods. And then the other thing that's highlighted today was the sort of data quality and research integrity throughout the whole process of research and experimental designs. And if you think about the whole series of experiments that Tim was talking about that might be part of a major paper, there can be lots and lots of those experiments presented in one paper. And really there needs to be, it isn't just about looking at the final results, it's about being clear, what are you going to do when you get the data and not effectively trimming the data when something comes through that you don't like or that you're chasing, particularly. So these terms here really got a lot of attention with Ioannidis' 2 publications, where he very sort of provocatively said that most published research findings are false, and then the later paper, why most of those true associations are actually inflated. And he did that mostly on a sort of an abstract way of saying, well, if these were the priors, this is what you'd expect to see. What's interesting is that that's been borne out to some extent with the various reproducibility. So the p-value gets a lot of stick, continues to be a bone of contention. So I've got a few slides in here to remind us what the p-value is. One of the simplest things that you can calculate. We've been able to calculate this for a long, long time before we even had computers. Part of this statistical hypothesis testing framework, and it's helpful to remember this. You've probably seen a slide like this in your lectures. What we really want to know about is this truth. We want to know, is really something really true or not? in a population. So this could be children aged 5, could be cancer patients, colorectal cancer patients, or a specific population that you want to know good information about. And the question, is one of these treatments, is this new treatment better than treatment B? For all sorts of reasons, you can't measure everybody in the population. So you have to take a sample. And again, I think this is where some of the problems in the reproducibility field, sort of conceptually, you take a sample, you get data, and you can summarize things about that sample, and they're all true. The data is your data. Where we get into difficulties is when we then try to infer something about this population from the data that we've got in the sample. And this whole framework is modelled in such a way that we just try to limit how many mistakes. Our type 1 and type 2 errors. So at the point when you get your sample, the model gives you the data related to this research question, you apply a test, and then you get your outcome. And so that's reminding you that the whole hypothesis testing framework is trying to infer something about a population that's not easy for you to see from a sample. And there are these stages in the hypothesis testing. First of all, you formulate this null hypothesis. Obviously, if we were interested in is treatment A better than treatment B, our null would be that there is no difference between these two treatments, that they are the same. And we will continue to assume that they are equally effective until we've got evidence to change our mind. Here's this significance level. So that's often that 5% that we're familiar with. You then select a sample, get data, reduce it to test certificate. Do all these things, and then the final thing is usually when you're getting taught this in your lectures is at the end you make a decision. And I think that's where some of the additional difficulties arise. So I said before that what we're trying to do is, as we can't really see that true full population, we have our null hypothesis that we're hoping to get evidence against, and then we have this alternative hypothesis. And so here we have the true situation in the population. So it's either true or it's false. So if the null hypothesis is really true, based on our sample, we can either reject it, or we've made a wrong decision, or a wrong inference, or we don't reject it and we've made a correct decision. And similarly, if the null hypothesis is really false, and we reject it, then that's good. But if we fail to reject it when it is false, then we've made another type of error. And a lot of the literature that we see looking at the sort of patterns in reproducibility are really telling us that what we thought our type 1 error rate is not right. And also what we thought our type 2 error rate is not right. So it's also important to recognise that this framework, this approach works for one question at a time on one data set. Okay? And really this hypothesis testing framework, the way it's constructed and the way it gets regularly used, and a lot of people disagree with the way it's used, but that's the topic for another talk. This is how it is frequently implemented. So if we set these error rates of alpha and beta, so alpha is very commonly set at 5%, and beta is commonly set at 10 or 20%. We're accepting that some of the time we're going to make mistakes. We are going to draw incorrect conclusions. And that's what Marcus was referring to in his talk, saying we can't just get more and more and more evidence. You know, different situations you might be able to act on weak evidence, or other situations you might want more and more evidence. So we are setting these parameters at the sort of error rate. And these, unfortunately, because of the way it's set up, this should hold, if we're all acting really, really well, these error rates should be then getting controlled over all our work as we conduct experiments and do analysis and draw conclusions. Unfortunately, we never know on an individual experiment basis if we've really made the right decision or not. We've only got a probabilistic summary that advises us how unlikely you are to see the data if the null hypothesis was true. That's all that we need done. And I think another reason why p-values are popular or remain popular is they're a single summary statistic. It's just one number. And we're in the olden days, when some of us had our training, but I still, even more recently, it's very common to do a statistical hypothesis test. And at the end of the test, you may just get a p-value, and not necessarily much more information than that. So it's already been mentioned today by many of the other speakers that while the p-values are helpful in us trying to quantify the state of the problem or how well our methods are working, it's really, really not that informative when you come to publish and report on individual studies. The p-value of anything is really not very interesting. It's the actual effect size and the confidence interval that's much more informative. It tells you about the direction of the effect. So if you do a test, you get a small p-value, but that doesn't tell you if A looks better than B or B looks better than A. The comparative statistics, for example, something like a mean difference with a confidence interval, can actually tell you much more information than you need from just a p-value. And actually, you can already infer whether a p-value is below 5% just by looking at the confidence interval. And if you use one of the methods listed here, well, this slide is telling you about some more what people might think of as more sophisticated forms of statistical analysis, where you may make more assumptions, where you may have more measurements at hand. So you can do here, you can identify the difference between two treatments while controlling or adjusting for many other factors. And you should always, you just have a few take-home messages. If you are doing any comparative analysis, you should really always aim to report effect sizes with confidence intervals at the end of any research, which is, I think, if you look at the reproducibility project, it was down in the protocol, wasn't it, that you reported the effect sizes with confidence intervals. But I think not all of the papers had originally produced those in the original report. So you couldn't even show them together on a graph. You probably had to recalculate those for the second. So Marcus had already referred to this, this paper, which is highlighting the problem with underpowered studies. And the problem with underpowered studies is that it has a whole host of problems. You might think, if you aimed to have a power of 8, that means that if there really was a true effect in the population, you've still got a 20% chance of not seeing it. You're not guaranteed to see it, even you've got an 80% chance. So if you're lower than that, you're actually really not making good use of time. So the difficulty with underpowered studies is that you get unpublishable results. Often, if they do show a significant difference, because they're very small, they're likely to show very inflated values and be very poor in precision. Sometimes the effect that you see is called a winner's curse here, when the first study showed a very big effect, whereas that's replicated much lower. And then when you couple that with the publication bias, sort of pressure, then underpowered studies really just contribute to what Ioannidis was talking about. So we really need to avoid underpowered studies, but that's, in a way, that's a bit of a quick fix because you just need to do bigger studies. So the real problem people seem very fixated on are actual p-values. And I think maybe at the end of the hypothesis testing framework about this making a decision. So I'm sure you've seen before a sort of a scale on how to report p-values in these windows. You've got like very, very strong evidence against the null hypothesis, weak evidence against the null hypothesis, etc. And this is really how you should see the results. At the end of your own, if you've run an experiment, you get a p-value of 0.06, then I think that's not negligible evidence, but it's marginal evidence. But it's actually very hard. You'll find if you try to get that published in journals, might want you to say, no, this is not statistically significant and therefore it's not important. And actually, in the grand scheme of things, if you've done a well-designed study with good power, then I don't see why you shouldn't be able to publish that with a p-value of 0.06 and it just gets out there. So I think we need to bear that top part in mind. I've already said that the p-values alone are not that informative, so you need to be reporting more, certainly the confidence interval around those measures. But then these other sort of ways that p-values can get used in an inappropriate way is that people can maybe just collect some data, look at the p-value. Oh, I think I'll collect some more data, see if I get a more significant result, because I'm absolutely sure that this is a real thing, that my hypothesis is bound to be true, or that other people really might try to replicate it. But if you keep taking repeated looks at the data, then the rule about the error rate is lost, and you're actually going to be increasing your rate of making wrong conclusions. So you don't want to be making data collection decisions based on interim p-values. And similarly, you shouldn't be making any analysis method decisions based on p-values. So both of those bottom two really do lead to biased results. And the p-hacking and flexible analysis, I probably talked about this earlier, but these terms are just used when there are some choices. So our number there is in italics because it'd be fine if the number of choices that you had was clearly stated, that'd be fine. But lots of different possibilities are tried, but then it's not reported. So for example, the difference between using a parametric or a non-parametric. And then so even the data trimming type one that, who mentioned that before, the data trimming, was that Marcus? Or was you, Tim? Yes, so unfortunately there's one of the packages that's commonly used that has a lot of nice features, GraphPad Prism, makes it a little bit easy to remove single data points from the analysis. And I said before that statistics does come with toolkits to allow for multiple testing and still control your type 1 error rate. So there's other communities, like in the genomics community, where it's well understood about the multiple testing and how to adjust that sort of threshold p-value to protect yourself in the long term. But if it's multiple testing, and particularly maybe splitting the data and looking at multiple subsets and only declaring the subset that looked interesting, again, this is going to just lead to too many positive reports. So what's been interesting to me in this process is that frequently when the waves come through of concerns about reproducibility and poor practice, there's often calls for sort of more methodologies, particularly statisticians, to get involved in research, because it's perceived that the statistics are getting used wrongly. And they are getting used wrongly, but not necessarily. I think what's at the root of the reproducibility crisis isn't really sophisticated methods getting used wrongly. It's maybe just simple methods getting used in a way that's unclear. So while obviously I'm biased, I always think that if you have a statistician involved in a study, it's going to be a lot better. But many people aren't really used to working that closely with statisticians, or might not even know any. So I'm going to ask those in the audience, are there any other statisticians here? I should have asked that at the beginning. Are there any statisticians here? Does anybody does anyone have a statistician who works with their team? Oh, right. So does anybody ever met a statistician who might occasionally advise their group? That's two, very good. Yeah, so that's interesting, because it can be really difficult to strike up those good relationships with statisticians. And as I said, in my own journey, where I was getting approached by people who knew they needed help statistically, but I couldn't quite understand their data. I was interested to see how things work better in the clinical trials. It's one example in the clinical trials context. It's much more common to work regularly with statisticians who really understand what we do. So what I'm trying to say is that statistics, the problem here, so I've said already, for the underpowered studies, we can just use bigger samples, okay? That should solve that problem. But for the p-hacking and flexible analysis and migration effects, you know, how can we really control that? And the best way, well, the first thing to do is just to stop doing those things. Just do one thing, okay? And these problems can be completely controlled by stating ahead of collecting your data how you're going to handle everything. That includes data quality, decisions about whether something's worked or not. You just state ahead, or you state very clearly. But it has to be ahead of when you see the data, because writing it afterwards doesn't really guarantee that that's what you did. And the other thing to be aware of is if we do that, if we just state ahead before you run your experiment and collect anything, that you just write down what you're going to do, that will control the type 1 error rate. Okay, that will mean that as you run experiments in the lab over and over again, that will be controlled at the 5% rate. Because actually, if you don't choose the best method for the analysis, you could actually be underpowered, because you said you're going to do something in your analysis. It's not very efficient. So really, if we want to improve this second part, that's where we actually need to be talking a lot more earlier on about all the elements of the design stage and improve that. And that's what Marcus referred to in his slide about the registered reports. You write down the protocol, and somebody gives you feedback and says, actually, I think this could be improved here. So it's this, the writing it down is the first part. That will help you with your type 1 error rate. But actually, if you want to have really well-carried studies, you need to work more on this forward protocol and the decisions that you're going to make conducting trials. And so I think people that aren't that used to working with statisticians might be surprised to find out all the things that a statistician would love to talk to you about before you actually come with any data. People are often aware that you need a statistician to help you with your sample size and power calculations. But speaking from my own experience, I often get asked about those things in complete isolation with what maybe the whole programme of work is. It'd be nice to know what the stages of the work that you're going to do. Are you going to reuse these samples many times to ask similar questions, or are you going to generate new data each time? And the things that a statistician is really going to want to talk to you about is all of these elements. So you've got blinding and masking. How are you going to get this in? I mean, it's not really a statistical thing, but this is what statisticians are very worried about. And they all like to ask you about all of these things, which could well be really quite overwhelming. I understand that when you first meet somebody. But really what they're after is to try to get, what you want is really efficient design. If you've got a very clear question and you really understand what are the constraints of what you're trying to do, what sort of data can you get, what equipment have you got access to do your measurements, you might be able to make all sorts of suggestions that would actually result in a more efficient design. And it would involve many people being involved in the discussions. So this is one of the things that I was involved with in the NIHR statistics group. And actually this is how I got involved in the reproducibility work. So we had this interest in the NIHR statistics group where laboratory-based researchers were asking for more access to statistics. Because of this work, eLife approached me because they were wanting to do better transparency reporting of statistics. And then I got involved as a reviewer for the pre-registered reports for the cancer reproducibility project. So we wanted to try to bridge this gap of statisticians really wanting to be able to give good advice as opposed to just, yes, if you think you want to detect a difference between two means of half a standard deviation, this is the sample size that you need. We wanted to try to break this down so that you could have a series of conversations with researchers about the elements of all the experiments that we're planning, and really to help understand each other's languages, and also to make it not quite so overwhelming to get all of these questions. So we formed, it was one of the first things that the statistics group did, was form this consortium where we actually went out and met, invited scientists, lab-based scientists to come and meet with us and practice letting us talk to them, and then they practiced talking to us. And we were sort of observing these conversations, and we set out this, this framework, which was a series of topics, subtopics, and then sort of questions that you could just come back to time and time. You didn't even need to have a statistician present. You could just look at these issues in advance. And we were very delighted with this, and I would encourage you to go and look at this in eLife. We were delighted because we felt we had a lot of scientists on board, but what I wasn't delighted about was just how long the paper is. And I want to apologise to you on behalf of all statisticians who try to do tutorial papers and short papers to break down the barriers to statistics, because these papers always end up being far too long. Each time we've done this, so if anyone would like to join us to try to do a shorter paper, please let me know. So we still use this. We've had a lot of good feedback, and there's 3 examples in it where this sort of what conversations might be like if you had an experiment like this. But it's really just meant to get conversations going. It isn't offering any solutions or any best methods. And eLife were really good, actually, about supporting this initiative. So in that document, in that very long document, it's got a sort of a framework table, and these are the sort of major topics. So these are the big parts, and the reporting results is just very, very minimal. And so just as an example of one of the sections, under the planned analysis section, we've got data assessment, evaluation. What are you thinking about here about how you're going to, what's your QC criteria, how are you going to verify data? Some of these prompts won't relate to anything that you do, and you can just skip over them. Then it's got a section on the statistical methods, thinking about these things ahead. So I'd be very pleased if any of you would have a look at that or had any experience of it to hear back, because we are planning some more events around that framework soon. So another output. So when we first met with the laboratory scientists, we asked them what would they like if we were going to do some tutorial papers. What would they like some tips on? And what came out top was the unit of analysis problem. I don't know if that means anything to you, but it basically means when you've got non-independent data. It often happens if you've got repeated measurements, or you may be doing replicates in some sort of experiment. And you can't then just throw all the data into an analysis package. You need to tell the program how the data are connected or handle it in a specific way. So we thought, oh, that would be nice, a nice unit of analysis paper. We'll just put 1 or 2 examples in there of how to handle this. And this one was meant to be sort of a methodological tutorial. I have to say it's still too long, but it has got some code in there. It has got a nice example. And Nick Parsons was the one that really drove that. On a related note, there's actually a very nice paper in Nature Neuroscience where they illustrate a similar problem when you've got nested data, where you've got correlation in the data, but they have the same data set and they ask several different questions of it. And it shows each time when you ask a different question, the way that you approach the data, the way that you analyze the data is very different. And that's really also a very nice paper. So just to show you what the example in the unit of analysis paper is looking at 12 patients with colorectal cancer. 6 of them underwent 12 separate patients. 6 of them had a short course of radiotherapy before their surgery, and the others didn't. And then there was a section removed, and each section was divided into 2 samples. So there's 6 measurements from each patient. So there were 2 sets of 3 measurements in each patient. So that was the example set of nested data that we used in that paper. So I think it's fair to say that the initiatives to really get more statisticians involved in this area. There's quite a few of us who are really very interested and keen, but I'm not I'm not feeling very convinced that it's really shifted. We've got these tutorial papers that come out, but I'm not sure how accessible they are, in fact. So again, it'd be very nice to hear from you maybe what you think you need some tips on to be able to do your statistical analysis differently. But at the moment, so I've highlighted in the talk the different reasons that statistics is getting a bad name, and there are a lot of cultural issues out there that we can't really push too hard against. And I've recently myself had the difficulty where we've tried to publish something that did actually have a p-value of 0.06. That was a clinical trial, and actually when we did the sensitivity analyses, it was hovering just above and below the 5% mark. And we had a big struggle with the reviewers, and they would not let us put in the abstract that this was a modest signal. We were not allowed to say anything about it being a positive signal, which I thought was very, very disappointing. But in terms of our daily practice ourselves, the things that we can control, I think it's nice to emphasise what we can do and be the best that we can be. So some of the things that I've listed here have already been mentioned earlier today. But the first thing I think is helpful, and I think when some of the problems arise in research, and it's in some of the papers more recently, I've noticed that we can have like hypothesis-driven research, but you might have a really, really broad hypothesis that doesn't just relate to one experiment. And the first thing that you need to do is break down your sort of big program of work. You might be doing a PhD, or you might be doing a big interdisciplinary project. But break it down into stages so that you can really specify what each stage is going to look like. And that each smaller component of the work will have a really specific research question. And then you need to, I said agree here because hopefully you're doing this as part of a team, but you need to decide with consultation how you're going to get the best possible data that you can from your experiments. Covering all these things, state how you're going to do the primary analysis, and then do this pre-registration as a protocol. And in that way, you have well covered yourself against inflating your type 1 error rate. And then I've got just another slide here that it picks out some of the good features from clinical trials, and I don't know really how much it's motivated by the fact that clinical trials really, really very expensive single experiment, and so there's a lot of motivation behind getting it right. And I don't know, maybe in the genomics field, which has come through and being a very highly collaborative field, but they have ended up sharing resources and getting a good model. I don't know how much of that has driven the better model there. But some of the things that can be mimicked maybe in small form, but not necessarily with all the intensity that you get in a clinical trial, is that they do have, from day one, everybody who's interested and got any role in the project is involved in all the decisions really early on. And that's very important, not to make decisions about your experiments in isolation. Very early on, they're very specific about this PICO framework. What is the population? What's the intervention? What's your comparison? And what are your outcomes? And that's very helpful because that in itself will lead to a lot of discussions where people say, no, I disagree. I don't think you should be measuring the outcome at day 7. It should be day 14. And then you have a really good discussion about which one should it be. They have a fully specified protocol. I don't think you would necessarily want to have a 150-page protocol, but they do write down explicitly what they want to do, because usually they are involving other centres in running these trials. So you have to have a really specific set of instructions that others can follow. And that in itself covers this sort of generalisability concern. They do have a statistical analysis plan written quite fully. These can be 70 or 100 pages of statistical analysis plan. They don't need to be that long in terms of what we're talking about here. But they are written before any data is collected. And then they also have oversight committees that are allowed to see the unblind data so that if something is going a bit wrong early on, then it can be corrected. That's usually about safety, but it can also be about there's too much missing data coming through in this outcome. This isn't going to work. So you can get an early signal that actually what you thought was the best possible design isn't. And then how are we doing this time? Okay, I'm just going to finish in the last few slides. Something that I think is really important is how we display results. And I think one of the benefits of all the concerns about reproducibility is that we have got used to seeing multiple results all being presented together in an easily accessible way. And I'm a great believer in the forest plot. I think forest plot can be used in many, many situations to communicate all sorts of things. It doesn't need to be used to get an overall estimate of an effect size. There's a nice paper here, which has just got a little tutorial in how to understand forest plot. And what you get, I think you get the perfect situation where you've got the data here in rows, and then you've got a visual representation of the summary analysis next to it. So if you're a number-focused person, you can look at the numbers, you can see there. And then you get your confidence intervals represented on this figure. So I personally like to use these a lot, and I'm very disappointed I couldn't use my own data here because one of the papers where I've used my own data is the one that we have in the difficulty with the p-value of 0.06. But in this top figure, for example, you can see, just from looking at this, you can see all the point estimates are above the null value. One of them is two of them are statistically significant because the confidence intervals aren't touching that null value. And then overall, this is your effect size and the confidence intervals are above the null value. Whereas here in the lower one, that's the wrong button again, sorry. Down here, you've got the point estimates going from ultimate size of this null value. It's not really looking that convincing, and here the overall effect size converts, not looking very convincing. So that's a little tutorial paper on how to read them. And this was actually used quite nicely. You can use, obviously, the forest plot itself can be used for any results at all. And it was used, I've shown here the results of the discovery trial when they looked to see if hydroxychloroquine was actually an effective treatment on COVID patients. It seems actually quite a long time ago now when the excitement about hydroxychloroquine was in the news. But the discovery trial was a platform trial where they were able to look at drugs as and when they came up. And they published the results here. So in this case, they've used the forest format. So they have got all participants is actually the lower part here because it's just the one trial of intervention, hydroxychloroquine versus the usual care that patients are getting with COVID-19. But what they've shown here is all the subgroup analyses. So they've shown by age, by sex, race or ethnic group. So each little sort of cluster is just one specific subgroup analysis. And actually what you can see here is that pretty convincing. Almost all of these point estimates are all in the direction of usual care better. So even though that p-value is probably, the p-value say 0.15, can't see it from that.
Yeah.
Yeah. So it's not tiny, but actually it's 0.15. I wouldn't call that marginal or weak. But what's interesting is that there's not a hint that this is of any use whatsoever, because all of the evidence of what the effect of this treatment is, it's not very good. It's really not very good. Definitely looks like usual care is better. I think that's one example of visually showing you, or visually communicating results in quite a nice way. So that's the end of my talk. Thank you very much.
Thanks a lot, Don, for your amazing talk. I think we have a few minutes for questions. Yeah, I'm going to start. One comment I've heard from people working in the lab is that maybe the work would like to have statisticians interacting with us in the lab and helping to design experiments. Would actually not be very stimulating and rewarding for statisticians. Could be like viewed as something as routine work, because it doesn't involve research in statistics per se, but just how to biologists who have not knowledge of statistics in their experiments. So what's your comment on that? What's your experience? Do you think that it would be, we could hope to recruit good statisticians to do this kind of work, integrate them in our labs? Would that be a stimulating work, or do we have to think of other options?
Thank you. Really good question. I think, well, first of all, you'd have to find a statistician who would want to do that. But I know many statisticians, all the statisticians in the stats, in my HR stats group, desperate to be able to go and then hang out in people's labs to see what it actually looks like, what they do. But the difficulty is who would finance that, because it could take quite a lot of time. And I think if a team decided to appoint a single statistician, it could be very tough in isolation. So what we've been trying to do is, we have recently appointed someone to our group who is working on laboratory-based designs, but we are still struggling. They're okay to let sort of see what they're doing, but they're a bit nervous about letting, because we wanted to go in, there's like all three of us to go in to see what they're doing, so that we could then come out of that and say to each other, no, I thought when they showed that graph, I thought that was showing this, what did you think? Because the difficulty is, the barrier is that it's very hard for the statistician to really understand what's happening. By the time you've said 3 or 4 times, I'm sorry, I don't understand, it starts to get a bit exhausting. So I think it's about just maybe taking an hour at a time, you know, maybe inviting someone to your lab meeting, one specific project, and maybe plans. It's nibbling away, but it is quite a jump for statisticians to join the team, maybe who aren't used to working with statisticians as well. And that's the difference. If you work in clinical trials, on a clinical trial with 3 statisticians, they all know the trial really well. Into meetings, they'll come out and say, you know what, I've just seen this come out. So-and-so has got a new way of handling missing data in this situation. You know, so as a group, you feel a bit more confident that you're doing the best thing. And it's quite a different situation in the lab with maybe only one statistician and a lot of divergent interests. And then, of course, the killer is how do you say to someone, oh, I'm not sure I would have done it that way? That can be quite tricky. That's the territory that I'm not convinced has been mastered very well. It does. Statistics is definitely embedded in certain areas really well, and then there's just other pockets.
I have one question if we have time, or two questions quick. Thanks for that talk. It was great. One thing, if you wanted to comment quickly, I think I know your stance, but I'd be curious to hear it, which is there's been some calls to decrease the threshold, right? Just say, oh, we'll help things if we just say get rid of 0.05 and make it, I think, 0.001, right? Or 0.005. So I'm just curious about like a little bit more of your thoughts on that push, although like I said, I think I understand. I think I know your stance is based on what I heard. The other one that, if you have time to elaborate, and actually your top paper that you're referencing there is it, which is, what is your experience, your thoughts on peer review and status, and like your role as a statistician in peer review? If you can, I'd be curious, we can talk about later, which is in contrast even to what you were doing with the reproducibility project, where we were asking you to review, or you was asking to review early versus the traditional way, which is all after the fact. So I'd just be curious if you have any like reflection on that as well. So I think that's probably how most people interact with statisticians, is they appear as reviewers.
Thanks. So shall I answer the second question first, because you don't have to remind me what this one was. But the peer review process is so difficult because statisticians are in high demand. And they get many requests to review papers, and some of them will take the approach that they just look in isolation at, are these numbers consistent? Does it look reasonable that you get a p-value from that data? They'll do a sort of detective work. Does this look right? Then you can get, which is the approach that I tend to take. I go in and say, right, what's the major message that these people are trying to communicate with their abstract? And where is the signal for that in the paper? And that's not commonly so commonly encountered. There's a whole divergent community, I think, when it comes to peer review. If you have a clinical trial and there's a protocol and a statistical analysis plan, then you should have access to those when you do the review, and that's helpful because you can refer back to it, or the authors can say, well, this, fair enough, we understand you're saying it might have been more sensible to do the analysis like this, but actually 5 years ago we said this is what we were going to do, and that's what we've done, and I'm afraid that's what's going to get published first, but we could maybe do your additional suggested analysis as a sensitivity. So I think the peer review process is very difficult because there isn't really enough time. There's not enough time for statisticians to really drill down. And while it's great that papers and that you can have supplementary method sections, supplementary everything, if you make it more and more things that the reviewer has to check. And I personally, as a reviewer, well, unless I'm like really suspicious, I wouldn't usually, as a reviewer, drill down and look at the actual data points, unless it was very simple, if it's 6. But I mean, I would always argue that if you've got really small sample sizes, your data should just be in dots on the graph. You shouldn't need to go and look in the file of your data to be able to. You can't really see everything from rows of data. So I think the peer review process could be massively improved, and I think really the journal and publishing community really should there is a project in Oxford. We've got like a peer review training program for statisticians, which has been funded, interestingly, by Cancer Research UK, which are the funders who are doing the registered reports. So it is quite tricky, and I don't really know what the good answer to that would be. would you say, when we get statisticians in the publication phase, it's almost a bit too late anyway? First question.
The first one was just if what your thoughts were on the p-value being reduced. Yeah, there's been calls that like that'll fix it if you just drop from 0.05 to 0.005.
Well, the immediate effect, provided people are still worried about power, is that it would definitely increase the sample size. But it's, I mean, if you think about the parallel in like drug trials in phase 2 and 3, or rather just the phase 2 part, it's much more common to have slightly lower power there, and that they're not actually worried about the type 1 error rate at all. So they might have quite a high type 1. So if you're doing more exploratory research, I don't think you really want to be forcing yourself to have a huge sample and you're really not sure. So I would be wary of really reducing the significance level. I think it's just more important to have higher power. But we definitely need some sort of threshold.
Thank you for this. Thank you for this presentation. I would say one thing, if I could go back in time and change one thing in my life, that would be learning statistics. So it's an advice for the students. You can't produce good biology if you are not aware to understand if your experiment is able to demonstrate something. So spend more time learning statistics. And I really enjoy your initiative of trying to create or recreate bonds between biologists and statisticians. And it's a real challenge because you have to create a common language between the messy biology and the ultra well organized statistics. So it's really I hope you will.
Thank you. And if anybody would like to join in more endeavours, or those of other groups that are trying to do this, I'd be really keen to hear from you.
I have a quick question related to the tutorials you mentioned and the repost and is there any meta-analysis or survey of the literature, especially for the lab work papers, the statistical methods? Basically, is there any empirical study to show how bad we are at doing statistics?
That's a tricky one, isn't it? I mean, I'm sure you're aware that at the same time we've got this reproducibility crisis and all of this, you know, bad stuff, most of our results false. There's a lot of negative messages going on out there, but and sometimes there are reports. So I think in animal research, for example, the McLeod's group in Edinburgh has definitely sort of quantified, actually, even though, you know, animal research is really quite tightly controlled and supposedly got high standards, actually an enormous amount of vagueness here. So I think I think the problem is more the vagueness and lack of specificity rather than real bad things. I mean, there are like the trouble is, you've got to have quite a lot of information to be able to do this a really bad thing, such as what Tim was talking about with the data game. I mean, sometimes you can see it. Sometimes you can see it, but you tend to see those sort of issues, I think, in where, oh, I should say this, but if sometimes the worst methods are seen if somebody like a clinician is having a short period in the lab doing a research project, maybe doesn't have a good grasp of what's happening in the lab, and then does some statistical analysis. You can see some really odd things being reported. So, I mean, I think in a meta-analysis, if you end up with really, really wide confidence interval in your meta-analysis, and both of the two things above. Narrow. I've seen that a few times. But I think it's I think in the big grand scheme of things, I'm absolutely astonished that it's actually 40% reproducibility when we look at things that are in the literature, because there's so many incentives to do things badly. Something is clearly working, unless we've got a biased sample, of course, unless we're only able to check the ones where we've got enough detail to check that it's been done well. But these replication studies, if we really had a true effect that's out there, we're going to be seeing them 80% of the time, and we've actually seen them 40% of the time. So people have been a bit over optimistic about that. I think that's quite remarkable. I mean, if I had one tip actually in terms of a core method, what people tend to do when they've got small samples is do a non-parametric test. And I would always recommend that you do your t-test first and make that your main analysis, because you'll get your effect size and confidence interval, and then do a non-parametric test just to see how much does the p-value change actually. And if it's a lot, then I wouldn't have much faith in that result. The t-tests are actually great. Don't be scared of using t-tests. Okay.
Yeah, I can ask just a very quick question. You must be aware, of course, about the N out of 1 clinical trials, you know, in the context of personalized medicine. And so that raise lots of questions about how to leverage the power of the already existing cohorts to be able to steal from some type of analysis. What is your feeling as a statistician on that?
Well, we should always be trying to, so there's many areas where it's a real challenge. If you've got a really rare disease or a very, very, very expensive potential treatment, you really want to be getting the best quality evidence that you can for any treatment. So I think all of the drives for more efficient designs are really to be supported, but they just need a lot of scrutiny and a lot of oversight. You know, the things like you mentioned before, like the basket type trials, where you're effectively borrowing information from other sort of subgroups. So in some ways, these sort of tricks that you could use in lab studies, you could say, well, based on previous results, I would expect my next results to look like this, having a sort of a Bayesian approach. And you know, you might not need quite so many samples, but you would need to be clear at the outset what was going to then be convincing evidence, and make sure that you could deliver.
Once again,